All right, so ionic compounds contain a metal and a nonmetal. Okay, we talked about that yesterday. Most of the time when we're naming an ionic compound, it's fairly straightforward. We name the metal, we name the nonmetal, we make the nonmetal end in "ide." Okay, it's pretty straightforward. The problems come in when we have a metal that has more than one possible charge. That is, it can give up more than, or has two different numbers of electrons that it can give away in a chemical reaction. Okay, we call those multivalent metals. So an example here, we'll look at number 6. Okay, we have mercury with astatine. So what we're going to do first is obey the normal ionic compound naming rules, and we're just going to write the name of the metal and the name of the nonmetal with an "ide" ending, and then we'll figure out what we have to do after that. So this will be mercury something astatide. All right, now the possible charges for mercury, okay, according to our periodic table, are 1 and 2. Okay, what we have to do is figure out whether this is the mercury with the 1 plus charge or the mercury with the 2 plus charge. Okay, how can I figure that out? Right, look at the periodic table and look at specifically the non-metal that is part of this compound, because the nonmetals only ever have one possible charge. So if I look up on my periodic table the charge for astatine, okay, I find that it has a charge of -1. All right, so that means every astatine is -1. And how many astatines are there in this compound? 2. So how many negative charges are in this compound? 2. Okay, so if every astatine is -1, -1 times 2 is -2. Okay, all ionic compounds have to have an overall or net charge of 0, which means there has to be 2 positive charges, and they have to come from where? From mercury, from the metal. All right, since there's only one mercury here, it can't be the mercury with a 1 plus charge, or this won't add up to 0. This has to be the mercury with the 2 plus charge. Okay, so this has to be mercury 2 plus. So then I would write the Roman numeral right here. This is mercury 2 astatide. All right, do one more example. Do number 5, just to kind of reiterate this. All right, so SN is tin. Okay, so I'm going to write tin, and then Te is tellurium, so this is going to be tin something telluride. Okay, possible charges for tin, according to your periodic table, are 2 and 4. Yeah. All right, so this could be tin with 2 plus, or it could be tin with 4 plus. We don't know. Okay, so I need to look at my non-metal. What's the charge for tellurium according to my periodic table? 2 minus. All right, so every tellurium has a -2 charge. And there are how many telluriums in this compound? 2. All right, so how many negatives do I have here? 4. Okay, so all I do, guys, is I find out what the charge is on my nonmetal, and I multiply it by however many there are. All right, so -2 times 2 is -4. All right, so I've got 4 negative charges that have to be balanced by only one tin. So is this the tin with the 2 plus or the 4 plus charge? If this is going to equal 0 and I only have one tin to do it with, I have to have the tin with the 4 plus charge. Okay, 2 will not balance off the -4. Okay, only the +4 will do that. So this will be tin 4 telluride. Okay, and have you guys try 7 and 8, and then we'll go over those. Okay, so I'll give you a few minutes here on 7 and 8, and then we'll look at them together. Okay, Roman numerals to at least 10. You're not going to need more than 10. Okay, so we have 1, 2, 3. It's simple to 3. Then after that, it stops making sense. Okay, then we have IV. That is 1 less than 5. V is 5. Okay, VI is 6. That's 1 more than 5. VII is 7. Okay, and then okay, we have 8, and then we have IX and X. Okay, that'll get you to 10. All right. I doubt you'll ever need more than 4. Okay, pretty rare that you'll ever need more than 4 for what we're doing anyway. Okay, so if you've seen, like, all the Rocky movies, they go up, pretty high. Yeah. Okay, Star Wars now, of course it's ruined, but what do you do? All right, so for number 7, okay, we have polonium. That's what PO is, so polonium. And it's with iodine, so this is going to be polonium something iodide. Okay, the charge on iodine is -1, and there are 4 iodines. So how many negative charges do I have in total here? I have -4. Okay, I only have 1 polonium, so its charge must be +4. Okay, that's the only way I can make this compound come out to 0, and that's what we always have to do, is make sure the compound has a charge of 0. So this must be the polonium with the 4+ charge, so that'll be polonium IV iodide. Okay. How many people have done number 8? Okay, let's have a look at number 8 then too. Okay, SB is antimony. Okay, and it is with sulfur. Okay, so this is going to be antimony something sulfide. Okay, sulfur's charge is always -2, and there are 3 sulfurs in this compound. So I have 6 negative charges here. That means that from the antimony, and I have 2 antimonies, I have to get 6 positive charges. What's 6 divided by 2? 3. So the charge on antimony must be +3. Okay, so this is going to be antimony 3 sulfide. All right, try the last 2 here. We'll go over those in a minute. All right, so for number 10, we have nickel with nitrogen. So we'll first follow the proper naming rules here. This is going to be nickel nitride. Okay, then we have to figure out what the Roman numeral will be. Nitrogen always has a -3 charge, and there are 2 of them, which means we have a total of 6 negative charges in this compound. Okay, nickel, okay, there are 3 nickels here, and I need to get +6 out of that. So what's the charge on each of the nickels? +2. Okay, so this is going to be nickel 2 nitride. All right, and then for our last one, we have ruthenium with oxygen. So this would be ruthenium something oxide. Okay, oxygen is always a -2, and there are 2 oxygens, so that gives us 4 negatives. So that means since there's only 1 ruthenium, it must have a charge of +4 in order to make that equal out to 0. So this is ruthenium 4 oxide. Okay. All right, so the big thing with naming ionic compounds is remember to name the metal first and the nonmetal second, and always check to see if the metal has more than 1 charge before you think you're finished. Okay, just in case you have to look for a Roman numeral. You don't always need a Roman numeral because not all metals have more than 1 possible charge. Okay, everybody with me there? Oh, you know what? It's because when I made this worksheet up, I had a different one. Some of them say it has more than 1, like this one up here. Okay, says that it can be 2, 3, 4, 6, or 8. Yeah, okay, so slightly different. Yeah, all right. Then let's talk molecular compounds. Okay, so molecular compounds are going to be made up of 2 non-metals. So that is 2 things from the right-hand side of the periodic table or right-hand side of the staircase. Okay, where ionic compounds had weak bonds where electrons were traded or given away, molecular compounds have incredibly strong bonds that we call covalent bonds. That is, they share the electrons. So they get their full outer shell, which is what the ionic compounds wanted. Okay, each thing wanted its full outer shell. The difference is that molecular compounds get their full outer shell by sharing the electrons, which means they can't live without the partner they have. Okay, if they split up, then they don't have a full outer shell anymore, and they'll be incomplete. Okay, I don't know, I keep going like sociological on you here, but okay, it's this sharing that makes the bond incredibly strong. So molecular compounds have this shared electron bond that makes them difficult to break apart. Okay, which is why a lot of molecular compounds are less soluble in water than ionic compounds. It's also why when you dissolve a molecular compound in water, the solution will not conduct electricity. Okay? If you dissolve an ionic compound in water, it conducts electricity because there's positives and negatives floating around in there. You have a molecular compound and it dissolves in water, there's no charged particles floating around. It stays together. Okay? Without those charged particles, okay, it won't conduct electricity. Incidentally, that is how, if I gave you like a sample of sugar and a sample of salt, so you can't taste it, but you got to tell them apart. That would be the way you could tell them apart. All right? They look fairly similar, both white crystalline solids with small grains. Okay? But if you put them both in water and dissolve them, one of the solutions will conduct and the other will not. Okay? Sugar won't, because sugar is a molecular compound. It contains carbon, hydrogen, oxygen. Okay? Whereas salt is sodium chloride. That's an ionic compound, and it would. Right? So there's that kind of big difference between the two. All right, so the big thing we have to remember here, okay, is that molecular compounds have covalent bonds. That is, electrons are shared. Okay, and you can see that here in the water molecule. Okay, so for oxygen, oxygen normally has 2 open spaces in its outer shell. That's why it has a charge of -2. Okay, so when it bonds with hydrogen, it shares hydrogen's only electron. So now its outer shell is full. Hydrogen has an outer shell that has 2 in it. It's full. Okay, and everybody's happy as long as they stay together. All right, everybody okay with that idea? That's essentially all you need to know in terms of how molecular compounds work. In terms of naming molecular compounds, these are the ones that use prefixes. And they use prefixes because there's no charge balancing to do here. Okay? With ionic compounds, we didn't need to use prefixes because there was only one way that things could go together and work. Okay? But with molecular compounds, they could go together in any number of different ways. There's no way to balance charges because everything is negative. Okay? I can't just keep adding negatives together and make it work. Right? It's like saying 2 wrongs don't make a right, but 3 do. Not really. That was supposed to be funny. Totally missed you guys. Okay, so what we have here is a case where we cannot balance charges, so we have to use prefixes to tell people there's this many of this molecule, or this many of this atom, and this many of this atom in this compound. All right, so examples could be, if I have carbon and sulfur together like this, CS2, this would be carbon disulfide. All right, or for this one here, actually this one has a mistake in it. Okay, this would be dinitrogen monoxide. Right, I put prefixes on to denote how many of everything there are. Okay, now the prefixes, just so that you have them. Okay, the prefix for 1 is mono. The prefix for 2 is di. The prefix for 3 is tri. For 4, it's tetra. For 5, it's penta. For 6, hexa. For 7, and this one's important, because if you ever took science in French, you were told this is septa. It is not, and the chem guys here hate that. So it's hepta. Okay, hepta. 8, octa. 9 is nona, and 10 is deca. Okay, we won't need to go beyond that for our purposes. So when we're naming molecular compounds, we always use prefixes to denote the number, except if the first element is a 1. Okay, We never start a compound with mono. Okay, we just don't. I don't know, chemists just have to be difficult. Okay, so they have to have some special exception. Okay, which is why on some of these, okay, you see like this one here says carbon disulfide. It doesn't say monocarbon disulfide. Okay, so we don't use mono on the first element, but we use it on everything else. Okay. Okay, everyone all right with that idea? So like I say, naming the molecular ones is pretty easy as long as we remember the prefixes. All right, so I'm going to have you guys do a couple here. Okay, we'll walk through the first two. All right, so on our first one here, I've got nitrogen with iodine. Okay, so when we write this out, we write the name of the first element as it appears on the periodic table. We don't alter it. Okay, but we do alter the last one. Okay, because there's only one nitrogen, I don't need to put a mono here, but I do need to put a tri in front of iodide. Okay, our second element always ends in "ide," regardless of whether it's ionic or molecular. Okay, second element always ends in "ide." So this is nitrogen triiodide. Okay, and then for our second one, I have one carbon. So again, I don't use mono on the first one. So this is going to be carbon tetra, because there's 4 iodide. Okay, I'll have you guys try the next 4 here, and we'll walk through those together. Okay, so for question number 3, I've got 2 nitrogens. So this is going to be dinitrogen, and then I have 3 oxygens, so that'll be trioxide. All right, questions on number 3? Okay, for number 4, I've got tellurium and acetatide. There's only one tellurium, so I don't need a prefix on that. So we'll have tellurium diacetatide. Okay, questions on 4? Okay, for number 5, I've got 2 phosphorus, so this will be diphosphorus trisulfide. Okay, and for number 6, I'm going to have oxygen monosulfide. Okay, questions on either of those? All right, let's have you try a couple more here, and we'll go through those. So do up to number 10. Okay, so for number 7, I've got 3 silicones, so this will be trisilicone. Okay, tetraphosphide. Okay, what do you notice about all of the names so far? What have I not done to any of them? No capitals. Remember, no capitalization. These are not proper names. Okay, it's a hard habit to break because we want to capitalize everything. Okay, number 8, I've got 1 sulfur, 2 chlorines, so this will be sulfur dichloride. Okay, for number 9, I've got 1 silicone and 4 hydrogens, so this would be silicone tetrahydride. Okay, and I know that hydrogen is acting as a non-metal because it's listed second. Okay, and then I have 4 borons, so this will be tetra boron tricarbide. A lot of these compounds probably don't exist. They're just naming exercises. Okay. All right. Any questions on any of those? All right. So reality of naming compounds is you're probably not going to be given a list that says, hey, these are all molecular. These are all ionic. These are all ionic but need Roman numerals. You're going to have to be able to identify which ones are which. That's the reality we're going to be facing here. So here's a list of some of everything. Some of them are ionic. Some of them are molecular. Some of them, none of them will require Roman numerals. But there's something in here that we haven't talked about yet. And we're going to use number 9 to talk about it. Okay. Every other compound we've gone over only had 2 elements in it. Number 9 has 3 elements in it because it's got what we call a polyatomic ion in it. Okay, that is a charged, yeah, sulfate, a charged particle that has more than one atom in it. So polyatomic means many atoms. On your table, periodic table, you will see a table of common polyatomic ions near the top on the left-hand side. Okay, so in there is a list essentially of the common polyatomic ions that we might encounter. We treat them just like we would a non-metal element, okay, because all but one of them is negatively charged and would behave thus as a non-metal. Okay, the only one in there that is positively charged is ammonium. That's NH4. That one behaves like a metal because it's positively charged. All right. So if I'm naming this compound here that has a polyatomic ion in it, it's actually quite simple. I name it just like I would any other ionic compound. First, I name the metal, and then I name the nonmetal. The name of SO4, according to your table, is sulfate. And that's it. That's all there is to it. Okay, I just have to write the name of it, and that's it. Okay, everybody all right with that? So actually the naming part's really not all that tricky. It's when it comes to doing the formulas and we have to drop and swap, then we might need brackets. That gets a little bit different, but it's not really that hard. Okay, we haven't got to that yet, but we will. So I want you guys to try all 14 of these. I will go through a few at a time. Okay, in a few minutes, we'll go through a few more and see how we're doing on this. Okay, so first step in naming any of these is first off to identify, is it ionic or molecular? Okay, how do I identify whether it's ionic or molecular? Right, I just look for a metal. If it has a metal in it, it's ionic. If it doesn't, it's molecular. Okay, so that tells me what rules I have to follow once I've done that. Okay, since this has lithium in it and lithium's a metal, this is an ionic compound, so I'm not going to have any prefixes. Lithium also only has one possible charge, so I won't need any Roman numerals. Okay, I don't have to do any of that stuff because lithium only has one possible charge. So this stuff will just simply be named lithium chloride. Okay, again, no capital letters. All right, for number 2, okay, I've got chromium and fluorine. Chromium is a metal, so this is an ionic compound. Okay, does chromium have more than one possible charge? Okay, what can they be? It's 2 and 3? Okay, so, sorry, there is one that has a Roman numeral in it on here. I forgot about this one. All right, so we got chromium here with fluorine, so we'll write out that this is chromium something fluoride. Okay, and then we have to figure out whether this is the 3+ chromium or the 2+ chromium. So every fluorine is -1. So there are 3 negative charges here. I need to get 3 positive charges from 1 chromium atom, so it has to have a charge of 3. Okay, this is chromium 3 fluoride. Okay, questions so far? All right, number 3 has phosphorus and bromine, both non-metals. So this is a what kind of compound? It's molecular. Okay, so I'm going to follow the molecular naming rules. I don't put a prefix on phosphorus because there's only one of it and it's first. Okay, but I do need a prefix on bromine. Okay, so that's going to be tribromide. Phosphorus, tribromide. And then number 4, I have zinc and iodine. Zinc is a metal, so this is an ionic compound. Zinc only has one possible charge, so this is just zinc iodide. Okay. All right, I'll give you a couple more minutes and then we'll do the next 4. All right, so on number 5, okay, we have silicone and oxygen, both non-metals. So this is a molecular compound. So this will be silicone dioxide. Okay, number 6, we've got 2 non-metals as well, carbon and sulfur. There's only one carbon, so we don't need a prefix on that. So we'll have carbon tetra sulfide. Okay, for number 7, we have technetium and iodine. Technetium is a metal. Okay, so this is an ionic compound, so we have technetium iodide. Okay, number 8 has a polyatomic ion in it, okay, because it has 3 elements in the compound. All right, the metal is sodium, so I just write that, sodium, okay? And then I have to look up what OH is on my table of polyatomic ions. OH is called hydroxide. So this stuff is sodium hydroxide. It's the active ingredient in oven cleaner. Okay, so if you've ever sprayed the white foamy stuff inside your oven, okay, that's what you were using. It's very, very basic, yeah, and it will dissolve basically anything, especially the cooked on crud inside your oven. You don't want to get it on you. Even smelling the fumes can burn your nasal passages and lungs. It's really nasty stuff. Okay. All right, how many people are done to, let's say, number 12? All right, let's have a look at those then. So for number 10 here, again, we have another ionic compound containing a polyatomic ion. Okay, K is potassium. So we just write potassium, and then we look up what MnO4 is, and that is called permanganate. Okay. Potassium permanganate are little purple crystals. They used to use them as a fungicide. And if you had like athlete's foot or something like that, they would put potassium permanganate crystals in water and you would soak your feet in there. The only problem with potassium permanganate is the little purple crystals don't stay purple when they come into contact with human tissue. They turn brown and like a dark brown. So if you have really light skin and you touch potassium permanganate, it will turn dark brown wherever you touch it, and it's quite noticeable and dark brown, especially if it gets on your fingers. People will wonder. Yeah, okay, because it looks like that. Yeah, looks like poop. Okay, like it's that color. I only know that because I had a kid when I taught back one of the second or third year I was teaching. This kid never listened ever, and we were doing a lab where we were using this stuff. And I said about 4 times, guys, don't touch the potassium permanganate because it'll turn your skin really dark brown. And this kid was like pasty. Right, like really, really pasty. And he never listened. And he comes up to me with the sample tray and he's doing this. Mr. Codere, these things are so cool. I'm like, yeah, they really are. Look at your fingers. And it doesn't come off. You can't wash it off. It stains. It like has to wear off. You have to exfoliate. Like this kid went home with sandpaper to try and get it off. Okay, like it took like over a week for the color to go away. So 2 lessons learned. Don't play with potassium permanganate, and always listen to Codere when he says don't touch that. Okay? Yeah. Okay, number 11. We got 1 nitrogen, 1 oxygen here, molecular compound. So this will be nitrogen monoxide. Okay, and number 12, we have beryllium, which is a metal. Okay, and this polyatomic ion Cn, okay, which is cyanide. So this will be beryllium cyanide. Cyanide is highly poisonous and interferes with the metabolic processes of your cells. Okay? It's not good for you. Hey, anybody done to 15? All right, I will give you another couple minutes and then we'll go through the rest of these. Okay, so for number 13 here, we have barium, which is a metal with, again, cyanide. So this is an ionic compound. So we would just call this barium cyanide. Okay. For 14, I have sodium with HCO3, which is another one of our polyatomic ions. Okay, this is sodium hydrogen carbonate. It's also sometimes called sodium bicarbonate. More commonly, it's known as baking soda. Okay, that's what this stuff is. So, sodium hydrogen carbonate. Okay, and lastly, okay, and sometimes we make a bit of a mistake with this one. Okay, this is a molecular compound, phosphorus with oxygen. However, on our table of polyatomic ions, there's also a polyatomic ion with exactly the same formula. Okay, however, we can only have phosphate in a compound with something else. This, because it's by itself, is actually its own compound and would be called phosphorus. Okay, tetra oxide. If instead it was in a compound with magnesium, okay, then it would be magnesium phosphate. Okay, but if it's not attached to anything else, then it's its own molecular compound. Okay, doesn't come up very often, but once in a while. All right, I'll give you a 3-minute break, then we're going to talk about going from names to formulas. Okay, we've been going from formulas to names, then we got to talk about going from names to formulas. So I'll give you a 3-minute break here, and then we'll do that. So the other way that this can go is I give you the name of a compound and you have to come up with the formula. This is actually what happens more often, okay? Especially if I give you a chemical reaction in word form, you'll have to write it out as formulas and then figure out what happens. That's where we'll be headed to, okay? So the first step in converting a chemical name into a formula is the same as it is for the other way around. You have to determine whether you're dealing with an ionic compound or a molecular compound, and the only way to do that is to look for the presence of a metal. If there's a metal, it's ionic. Okay, so if I've determined that I have an ionic compound, then my next step is to write the formula for the metal and write the charge. So just as an example here, so we can walk through the steps, we'll say that I've got this compound here, calcium phosphide. Okay, so they've given me the name calcium phosphide. So my first step is that I write the formula for calcium and indicate its charge, 2+. I get that off my periodic table. Then I write the formula for the nonmetal and I indicate its charge. Phosphorus has a charge of -3. Okay, now I have to balance those charges, and I do that using the drop and swap. Okay, so drop and swap works very simple. I drop the 2+ down and I move it over, swap it to the phosphorus. So there are 2 phosphorus. I do the same thing with the 3. I drop it down, I bring it over here. Okay, there is my new formula, Ca3P2, and I'm done. Okay, that's how it works for ionic compounds. The only thing we have to remember for ionic compounds, actually there's 2 tricks to this, okay? And it involves if I get numbers I can reduce, or if I have a name that has a Roman numeral. All right, so if I have, for example, this one, okay, I've got to write my formula out. So this is copper, okay? The formula for copper is Cu, and what's the charge on copper here? 2, okay? That's what the Roman numeral tells me. The Roman numeral is there to tell me use the 2+ charge when you do your drop and swap. All right, the copper is bonded to sulfate, which is a polyatomic ion. Everybody all right with that? Okay, so the formula for sulfate is SO4. And the charge on SO4, according to your periodic table, is -2. Okay, so when I drop and swap this, what I end up with is a 2 here and a 2 over here. Do I need to keep the 2's or can I reduce that to 1 and 1? 1 and 1. This is already balanced. 2+ and 2 negative already equal 0. Okay, so I just leave it in its simplest terms. Okay, another thing that could come up would be if I had, let's say, so I have another polyatomic ion here, calcium nitrate. Right, so I'd write out calcium, it has a 2+ charge, and I'd write out nitrate, that's NO3, it has a -1 charge. Okay, when I drop and swap, the 1 comes over here, but I don't write 1s, so I don't have to put anything there. And this 2 goes over here. What do I have to do around the NO3? I have to put brackets around it. Here's why. If I just do this, what does that compound say? There's 32 oxygens, okay? There are not 32 oxygens here. There are supposed to be 2 nitrates, okay? So if I need to put a number beside a polyatomic ion, I have to put the polyatomic ion in brackets, okay, in order to indicate that. Otherwise, I start getting crazy numbers that don't actually work. All right, everybody okay with that? So that's how the drop and swap works, okay? If you can reduce the numbers, you reduce the numbers. If you can't, you leave them as they are. Okay, molecular ones are super easy because molecular compounds already tell us what numbers to use because they all have prefixes in them. Okay, so I just go by the prefix and I indicate the numbers. All right, so if I have CS2, okay, I know that that's going to be carbon, or if I have carbon disulfide, I know I have 1 carbon, 2 sulfurs. If I have tetraphosphorus, that means I have 4 phosphorus. Decaoxide, that's 10 oxygens. I just write the numbers out. Okay, so it's the molecular ones are really easy. You just have to write out whatever number the prefix stands for. Right? Okay. Back up. All right. So what I want you guys to try here is, let's try 1 through 5 for right now. So this is working on, I give you the name, you got to come up with the formula. Okay, so let's try those 5 for right now, and we'll see how we do on those. Okay, let's have a look at a few of these here. I think we already did calcium phosphide. I think I actually picked that one by accident. But okay, so if I have calcium phosphide, okay, I write calcium. It's a 2+. Phosphide is a -3. So we got Ca3P2. Okay, as our formula there, we drop and swap it because it's an ionic compound. Okay, cesium oxide. So cesium is Cs. Okay, and it's +1. +1. Okay, and then oxygen is O, and it's -2. So when I drop this is an ionic compound, so I drop and swap. The 1 goes here. We don't write ones. Okay, the 2 goes here. So we got CS2O for our formula. Okay, for number 3, I've got a polyatomic ion in here, or sorry, not a poly, I've got a Roman numeral, sorry, in this one. Okay, the Roman numeral tells me what charge to use for my multivalent metal, which is manganese. So manganese is Mn, and they told me that it has a +4 charge. That's what the Roman numeral is there for. Okay, here's the biggest source of confusion for people when they're doing this. They assume the 4 means there's 4 of them. The 4 means use the +4 when you drop and swap. Okay, that's what we have to remember about the Roman numeral. All right, so I got manganese, and it is with oxygen, which is a -2. So this is going to be an example of a compound where we have to reduce our numbers after we drop and swap. So I drop the 4 and swap it over to here. I drop the 2 and I swap it over to here. All right, I have 2 and 4. Can I reduce that to 1 and 2? Yes, so I should. Anytime you can reduce, you should. So this is going to be MnO2. Right? Doesn't happen very often, but you got to be ready for it when it does. For number 4, same thing. I've got a Roman numeral here. So this is iron 2 sulfide. So that'll be Fe with S. The Roman numeral tells me use the 2+ charge for iron. Sulfur is always a -2. Do I have to even do anything here? It's just going to be FeS. Okay, the charges already balance out, so I don't need to do anything else. Okay, and then for number 5, we've got potassium permanganate. So potassium is K, and permanganate is a polyatomic ion, MnO4. That's the little purple crystals we talked about just a little while ago. Okay, potassium is a +1. Permanganate is a -1. Do I need to do anything with this? Nothing at all. Okay, do I need brackets? No, I don't need to put another number there, so I don't even need brackets for this one. It's just going to be KMNO4. All right, try, let's say, up to number 10 here. Let's see how we do. Okay, let's have a look at a few more here. So for number 6, I've got silver chloride. Okay, is that ionic or molecular? It's ionic, silver's a metal. Okay, so we got silver, which is a +1, chlorine, which is a -1. Okay, that's already balanced. It's just AgCl. We don't have to do anything else with that one. Okay, then we got copper 2 hydroxide. So definitely an ionic compound. It's got a metal and a polyatomic ion. Right, so we're going to have Cu, and the Roman numeral tells me this is the copper with the 2+ charge, is with hydroxide, which is a polyatomic ion, OH, and that has a -1 charge. What am I going to need to put around OH in this compound? brackets. Yeah. Okay. So what I'm going to end up with is CuOH2. Okay, for that one. All right, number 8 is the first time we're using the only positively charged polyatomic ion in our chart. Okay, ammonium is our positively charged polyatomic ion. Its formula is NH4, and it has a charge of +1. And it is with sulfide, okay, which is S, and it has a charge of -2. So when I drop and swap this, the +1 goes here, but we don't write ones. Then I'm going to have to bring this 2 and put it here. So what has to go around NH4? Brackets. Okay, so we're going to have NH4 bracket 2S. That would be ammonium sulfide. Okay. All right, then we got, for number 9 here, we got nickel 2 bromide. So again, an ionic compound with a multivalent metal. So this is nickel. The Roman numeral tells me use 2+ when you drop and swap. It's with bromine, which is a -1. So this is just going to be NiBr2. Okay. All right, questions on how that works? What do you suppose tomorrow's quiz will be on? This. So I will post that at 3:30 today. Make sure you check it out tonight. Okay, get a little bit of practice. We'll probably spend a bit of time practicing this tomorrow. Okay, after the quiz, and then we'll start looking at properties of compounds and things like that because we'll be doing our first lab early next week. Okay.